Hello, and welcome to my presentation, Nuclear Power, the Future of Clean Renewable Energy. Where do you think that the energy that you use comes from? Is it oil, natural gas, wind, solar? Chances are, even if your energy grid is connected to a renewable resource, according to the U.S. Energy Information Agency, as of 2015, up to 82% of the energy that you consume is still produced by fossil fuel. Well, why is this a problem? Well, competition for fossil fuel can cause geopolitical and economic instability. Proliferating the use of fossil fuels also pollutes the environment with harmful toxic waste and dangerous greenhouse gas. In fact, scientists are now warning that we are dangerously close to irreversible climate change because of our dependence on fossil fuels. If we are to have any chance to prevent this disaster, we must urgently seek safe, clean, efficient, and renewable energy sources to meet humankind's insatiable demand for energy. Is there a solution? Well, yes, there is. Today I want to talk to you about nuclear power. I became interested in nuclear energy as the result of a growing international conversation over climate change. Learning how the human demand for energy has played such a critical role in creating the urgent dilemma that is climate change has prompted me to research viable energy solutions that will power our civilization into the future. I strongly believe that nuclear energy holds the key to the future of safe, clean, efficient, and renewable energy. And today, I intend to convince you of the same. First, I'll discuss the pitfalls associated with the current standard for nuclear energy production, nuclear fission, and why that's led to an underutilization and stigmatization of nuclear energy. Then I'll explore the potential benefits and solution provided in an exciting emerging alternative means of nuclear energy production, nuclear fusion. There are two main ways in which we can produce nuclear energy. These are nuclear fission and nuclear fusion. Wikipedia defines nuclear fission as a nuclear reaction or process of radioactive decay in which the nucleus of an atom is split into smaller parts. For example, nuclear fuel such as uranium, plutonium, or thorium is bombarded with a subatomic particle, the neutron. When a neutron collides with the nucleus of one of these atoms, it breaks into smaller parts, including more free neutrons, in what's referred to as a fission event. Each fission event releases energy and can trigger another in a chain reaction known as radioactive decay. The energy released during radioactive decay produces heat which can be converted into electricity. Wikipedia defines nuclear fusion as a nuclear reaction in which two or more atomic nuclei collide at very high speeds and join to form a new nucleus. In this case, hydrogen would be used as a nuclear fuel. The fusion of the hydrogen nuclei results in a new helium nucleus with a lower atomic density than the previous two hydrogen nuclei. The difference in mass is released as energy in the form of heat, which can be converted into electricity. I'll explain why the difference of these two types of nuclear energy is so important. The current standard for nuclear energy production, nuclear fission, has earned itself quite a severe stigmatization, and not without reasonable cause. Chernobyl, 3 Mile Island, and more recently Fukushima are all the sites of fission reactor meltdowns. These terrible nuclear disasters have raised serious concerns about the safety and environmental impact of nuclear energy and are powerful examples of why it's so stigmatized. While it is an incredibly efficient source of energy, the problem with nuclear fission is it's not very safe. There are many potential dangers associated with nuclear fission. Because nuclear fission is a chain reaction, failure of a single component within a fission reactor system can result in a reactor meltdown, or a loss of control over the fission reaction. A meltdown can cause a breach in the containment of radioactive materials, leading to fallout, where radioactive material is released into the environment, potentially poisoning land, resources, people, and animals. In the event of a reactor meltdown, the reactor site and surrounding areas of fallout are rendered completely uninhabitable and are incredibly difficult and expensive to contain. In the case of Fukushima, for instance, containment of the fallout has proven to be an impossible task. As radioactive waste leaks uninhibited into the Pacific Ocean from a water table of a damaged shoreside facility, there simply is no effective means of mitigating the fallout. The efficiency of nuclear fission is overshadowed by its many drawbacks. While nuclear fission is an extremely efficient energy source, producing more energy per unit of mass than any available fossil fuel or alternative energy source, the benefit is outweighed by the cost in safety, cleanliness, and renewability. It's not clean. Uranium, plutonium, and thorium in fission produce a radioactive decay, resulting in a dangerous toxic radioactive waste. The half-life of these radioactive wastes ranges from hundreds to thousands of years, making safe storage expensive and impractical. And it's not renewable. Uranium, plutonium, and thorium are all rare earth elements, for which there is a finite supply, which will someday exhaust, just as we're beginning to exhaust our supplies of fossil fuel. Thermonuclear fusion has an enormous potential as safe, clean, efficient, and renewable energy source. New advances in fusion reactor technology will soon make indefinitely sustainable thermonuclear fusion a reality. Thermonuclear fusion is far preferable to nuclear fission because it's relatively safe. There aren't many potential dangers associated with nuclear fusion as a method of energy production. Fusion is not a chain reaction, so unlike fission, a meltdown is not possible. If a single component in a fusion reactor system fails, it would just result in the cooling of the reactor rather than the heating. And because of the shorter half-life of radioactive materials used in nuclear fusion, a potential containment breach would be far less disastrous. It's relatively clean. While some methods of nuclear fusion produce no long-lived radioactive waste, others produce none at all. The half-life of most radioactive waste produced by fusion is less than 10 years, and it's incredibly efficient. Individual fusion reactions have a much higher energy density than fission events, meaning that fusion produces more energy per unit of mass than fission. And it's renewable. The elements used as fuel for nuclear fusion, in particular hydrogen, deuterium, and trillium, are all found in abundance widely spread over the globe. Hydrogen and deuterium can be found in seawater. About 1 part in 5,000 of the hydrogen in seawater is deuterium. And trillium can be generated from lithium inside the reactor, and lithium can be found in rocks and also in salts extracted from seawater found around mineral springs. So in conclusion, we cannot continue to look to fossil fuels to meet our growing energy needs. Continued use of fossil fuels as our predominant source of consumable energy will only proliferate the geopolitical conflicts as a result of resources becoming more and more scarce. Furthermore, it will inevitably result in a dangerous and potentially permanent runaway greenhouse effect. If humans want to peacefully coexist in a habitable Earth in the future, we must find clean, efficient, and renewable energy sources that can meet our demands. And that source can't be nuclear energy. While nuclear energy has had a troubled past in nuclear fission, the pursuit of its development as a science has led to incredible breakthroughs in technology, providing a better and safer alternative in nuclear energy, nuclear fusion. Nuclear fusion holds the greatest potential to permanently release us from the bondage of fossil fuels and usher in a new era of safe, clean, efficient, and renewable energy production. Thank you.